we have a 20 gram bullet passing, being shot into a 200 gram apple. The bullet passes through the apple, comes out with a velocity of 200 meters per second. The apple has a velocity of 80 centimeters per second. The apple was initially stationary. So we want to calculate the speed of the bullet before the collision. Well, the momentum before, let's let V1 be the velocity of the bullet before collision. So we have V1 here. We'll indicate that next to the vector. Of course, this vector should be longer because clearly the bullet is going to lose speed passing through the apple. So let's not take the lengths of the arrows quite seriously. I didn't plan that out very well, but you know, you get the idea. So momentum before, well, the apple has zero momentum. It's stationary. I didn't write that down here, but that's in the statement of the problem. And the momentum of the bullet is 20 grams times its initial velocity, 20 grams times V1. That's equal to what? The total momentum after collision, which is 20 grams times 200 meters per second. 20 gram bullet. Bullet hasn't lost any mass. And we'll assume the apple hasn't lost any significant mass. Obviously, some bits of the apple are going to squish out here. We could take that into consideration, but just to keep it simple, we're going to make that assumption. 200 gram apple at 80 centimeters per second, well, that has momentum 200 grams times 80 centimeters per second. Well, we add up all the numbers on the right hand side. You got to do the multiplication, add up the numbers. We get 4,160 gram meters per second. Now, I went to meters per second. The 80 centimeters per second is 0.8 meters per second. This is 0.2 kilograms. Actually, I went to gram meters per second, so we don't have to worry about the kilograms. 200 kilograms times 0.8 meters per second is 160 kilogram meters per second. Added to the 4,000 gram meters per second we get from this calculation. And we still have the 20 grams times V1 on this side, but not for long, because we're going to divide that 20 grams into the right-hand side. Well, we divide both sides by 20 grams. This is what we end up with. And we conclude that the velocity of the bullet before collision would have been 208 meters per second. Just a quick additional comment. The kinetic energy after the collision is going to be less than the kinetic energy before the collision. This is not an elastic collision. Kinetic energy will not have been conserved, and you can verify that by calculating 1/2 mv1 squared. And of course that's just for the mass of the bullet, 1/2 mv1 squared for the mass 1. And then the 1/2 mv squared of the apple and the 1/2 mv squared of the bullet after collision. The total of these two kinetic energies will be less than this kinetic energy. And I'll add a final comment that we know the kinetic energy after is less than the kinetic energy before. How do we know that? We know that because the magnitude of the relative velocity after collision is less than the magnitude of the relative velocity before collision. After collision, and I don't have that right, let me fix the numbers down here. Here are the correct numbers. The relative velocity before collision, well, you got 208 meters per second and 0. That's 208 meter per second magnitude of the relative velocity. Afterwards, 200 meters per second this way, but also 80 centimeters per second, 0.8 meters per second for the apple. So the bullet is only receding from the apple at 199.2 meters per second. Okay, so relative velocity after, relative velocity before. And because of this, it follows that the kinetic energy after is less than the kinetic energy before. And we can go back to these three equations which have just been discussed to understand how that is and how that's equivalent. In any case, whether you accept this condition or whether you actually go ahead and calculate all the kinetic energies, which would be easy enough to do, Our conclusion is that the collision is inelastic because a completely elastic collision is one where kinetic energy is conserved.